We have seen how redshift surveys can be used to describe large-scale structure, at least in the cosmographic sense. But how do we quantify the distribution of galaxies such that we can compare with theoretical models? The first way in which people have done this is to use the so-called two-point correlation function. Nowadays, power spectrum is more often used, and the two are actually related in a very simple fashion. We will go about that next time. So let's talk about the galaxy two-point correlation function. What it means is that if galaxies are clustered together, they're correlated. Each galaxy is somehow more likely to be found next to another galaxy. And one way to quantify this is to ask the question, assume that galaxies are actually uniformly randomly distributed in space. Then at a distance from any given galaxy, there will be certain probability of finding another galaxy. If you actually measure this, you find out there is an excess. There are more galaxies near other galaxies than you'd expect from purely random distribution. And that excess above the random is what correlation function is. So one simply does the counting of galaxy pairs for each galaxy and then normalizes by what the random distribution with same number of data points would be. As it turns out, the two-point correlation function is well represented by power law, and it's usually written in this form, that radius divided by some scaling radius to some power, which is close to minus 1.8. And typically, for normal galaxies in this neck of the universe, the scaling length is about 5 megaparsec. This, however, is not universal. Different kinds of galaxies have different clustering properties, as you will see shortly. So here is an example of a modern, well-measured two-point correlation function for galaxies from 2DF redshift survey. It does look pretty close to the power law, although if you subtract the best fit power law, you see that there are some significant deviations from it. Now, if you don't have redshifts, you can measure the angular correlation function, just projected in the sky. And this two-dimensional projected correlation function, usually denoted with little w, not to be confused with the equation of state parameter, is related to the three-dimensional correlation function psi of r in a fairly simple fashion. The power law exponents differ exactly by 1 because we reduced the dimensionality of problem from 3 to 2. Another important point is that if galaxies are more likely to be found near other galaxies, there is that excess probability. Then in order to keep the average constant, it has to turn negative at some point. And it does, at scales that are roughly corresponding to those of voids seen in galaxy distribution. If there is a void in a distribution, in some sense, that's anti-correlation. It's less likely to find galaxy there than if it would be if the space was uniformly populated with galaxies. So how do we do this in practice? Suppose you have a catalog of galaxies from some survey. Then you can create a random catalog, galaxies, same number of galaxies, but randomly distributed in a Poissonian fashion. Then you can do the simple counts. Count galaxy pairs, one against the other, and count the fake galaxies pairs, the random catalog. Divide the two and subtract the 1 because it's the excess probability. For a large, extensive catalog of galaxies with uniform borders, this will work fairly well. But in reality, catalogs do have some incompleteness or uneven borders and so on. So there is a better estimator, which is called the Landy-Zalé estimator. And its formula is given here. We make a correction by counting galaxy versus random catalog pairs. This takes care of the boundary conditions. Now, if you're not counting individual galaxies, but have essentially a galaxy density field where you can divide galaxies in boxes or pixels, then numerical galaxy density can be used in the same fashion. You subtract the expected average from the actual count n and divide by the average. So if you do this for any kinds of pairs or density pairs, then psi of r is really the expectation value of this probabilistic distribution. Now, strictly speaking, because we're correlating galaxies with themselves, this should be called the autocorrelation function, but common usage is just to call it correlation function. Note also that you can correlate sample of one kind of objects versus the others. So for example, you could ask, are galaxies clustered around quasars? And then you can evaluate cross-correlation function between galaxies and quasars, and so on. By analogy, we can expand this to higher order terms. The three-point correlation function now asks, given a galaxy, given a probability of finding another galaxy at a certain distance, what is now probability of finding a third galaxy at some other distance? This obviously gets a lot more complicated and numerically tedious very fast. However, there is some useful information in these high-order correlation functions, and sometimes they're evaluated. I mentioned that different kinds of galaxies can cluster differently, and here is the simplest thing you can do. You can ask, how are galaxies clustered, say bright ones versus faint ones? And it turns out that bright ones are clustered more strongly. The amplitude is higher and the slope is steeper. The steepness of the slope obviously correlates with how strongly they are clustered. If the correlation function was perfectly flat, there will be no correlation. Understanding effects like this contains some useful information about galaxy formation mechanisms, and we'll talk more about those later in the class. Or you can divide galaxies by morphological type, say ellipticals versus spirals. Turns out that elliptical galaxies, or redder galaxies, are clustered more strongly than the blue ones, the disk galaxies. That too has some interesting clues about galaxy formation and evolution. So it's a power law. Does that mean it's a fractal? Remember, for any distribution of points, the probability of finding another one from the same set increases some dimensionality of that space. In normal 3D space, it would be like a cube of radius. If that number is not an integer, the set is called fractal. So we can write this formula, which is resembling correlation function. And if indeed it was a pure power law, then you could say universe was fractal, if it was a pure power law extending to infinitely large distances. But in reality, that's not the case. There are significant deviations from power law. It's slightly bent, and therefore universe is not fractal, or large-scale structure is not fractal, although it's pretty close to it. Next time, we'll talk about power spectrum of galaxy clustering, which can be directly related to theoretical predictions.